Welcome everyone to Reducing Campus Emissions and Energy Bills through Software-Based HVAC Optimization. Thank you for joining us today. This webinar is brought to you by Second Nature in partnership with Optimum Energy. The webinar will be recorded and the recording and slides will be sent to all registrants in the days following the webinar. There will be a Q&A session at the end, and you can submit questions directly for the Q&A at any time during the webinar by using the questions function in your GoToWebinar panel. Welcome everyone. I'm Brett Passanella, Senior Manager of Innovative Services in Nature, and thanks for joining our webinar today. Next slide, please. I just want to start off by thanking our sponsors that make the work of Second Nature and these webinars possible. Next slide, please. So Second Nature, this is our mission statement. We're working to proactively build a sustainable future. And we do that by initiating bold commitments, scaling successful actions, and accelerating innovative solutions. Next slide, please. And this is just a refresher. Our main program at Second Nature is the President's Climate Leadership Commitments. We have 3 commitments now. The climate commitment is our primary commitment, and that integrates both mitigation and adaptation by focusing on carbon neutrality and resilience in the face of climate change. We also have the carbon commitment, which focuses exclusively on aspects of climate action, and this is some of you may be familiar with the ACUPCC. The carbon commitment is the updated version of that. So former signatories of the ACUPCC, if they have not upped their commitment to take on resilience as part of the climate commitment, they have transitioned from being ACUPCC signatories to carbon commitment signatories. And we also have the resilience commitment. If a campus wanted to focus exclusively on resilience action and not take any mitigation aspects, they could sign that commitment as well. Next slide, please. And so today, I want to welcome Kevin White, Director of Business Development from Optimum Energy, and Kevin Koredish, Director of Optimization Services from Optimum Energy. So welcome, Kevin, and I'll turn things over to you for the webinar and be back at the end to moderate the question and answer session. Thanks so much.
Thank you, Brett. I wanted to start off by saying thank you to Second Nature for hosting us in this webinar. Optimum Energy is proud to be a corporate partner of Second Nature, and we look forward to helping more signatory colleges and universities get closer to meeting their sustainability goals. As Brett said, I'm Kevin White, Director of Business Development at Optimum Energy. I'd also like to go ahead and thank all of you who have taken the time to call in today. First, just a few words about who Optimum Energy is and why we're the world's leading provider of scalable HVAC energy efficiency programs for enterprise organizations. We have solutions that address waterside, airside, and even the boiler, providing up to 50% energy savings on HVAC. We have 200 installations in over 120 million square feet under optimization management. That's more chiller plant tonnage under optimization than all other providers. Our customers range from world-class universities to local hospitals to Fortune 500 companies. And together, we verifiably save them over 500 gigawatt hours of energy through our automated measurement and verification and online reporting platform. Next slide, please. A lot of you on the call today are in charge of sustainability efforts at your college or university, or in some fashion working towards making your organization more sustainable. And some of you might be wondering, why HVAC? Well, I think this chart tells the story. The fact is, there's justifiably been a lot of buzz around lighting in the last 5 to 10 years. It's relatively easy to put in LEDs and advanced lighting and save a pretty significant amount of energy, and therefore both carbon and dollars. But 2 important factors arise from this. The first is that, well, the low-hanging fruit is getting picked over a bit. So if you put in your LEDs, what's next? And the other important fact is that in the average building in the US, fully half of the energy spent actually comes from heating and cooling systems. That's over twice what lighting represents. And for buildings and campuses with chilled water central plants, they can be 35% of the HVAC portion, with Airside another 25%. So if you can make HVAC more efficient, it can lead to dramatic reductions in your energy use, your carbon emissions, and your utility budgets. Next slide, please. According to the U.S. Department of Energy, college and university campuses spend $14 billion each year on electricity. They also say that 44% of total campus electricity and 77% of total campus gas use goes towards heating and cooling. That's over $6 billion each year on just the electricity side. Even a 20% reduction would save higher ed institutions $1.2 billion each year in energy costs, not to mention the massive amount of carbon emissions avoidance. Next slide, please. What is optimization? Well, that's why we're here today, to talk about how you can use software-based HVAC optimization to dramatically reduce your energy spend and your carbon emissions. Optimization is definitely a big buzzword in the industry these days. And it seems like when you go to a conference, everybody's talking about how they're optimizing everything. But people often have difficulty agreeing on what optimization really is. Is it something that engineers do? Is it software? Is it hardware? I thought it'd be good to just take a step back and see what the dictionary has to say. It defines it as an act, process, or methodology of making something as fully perfect, functional, or effective as possible. I think it's the last part that is the most important, as effective as possible. So optimization is not just using less energy. It's not just being more efficient. It's about being as efficient as possible. This is very true in HVAC. Next slide, please. The 3 laws of optimization. We like to talk about the 3 laws of optimization at Optimum Energy, and I think this gives some really important context to what optimization means and sets the stage for some of the things we're going to talk about later. The first law is you cannot optimize what you cannot measure. If you don't know how well your HVAC system is performing, there's no way to make it as efficient as possible. You're just shooting in the dark. So making sure you have sufficient information, the right information, is crucial. The second law is optimize systems, not just components. We'll go into this in a little more detail, but the key here is that if you're looking at the performance of one component in isolation of what the other pieces of your HVAC system are doing, you don't have the whole picture. You might think that reducing a particular pump speed will save you energy, but in reality, that might trigger something somewhere else in your HVAC system to use more energy, resulting in net energy increase. So looking at the system as a whole is very important. And finally, the third law, optimization must be continuous, dynamic, and self-actuating. The reason that Optimum Energy was founded 10 years ago is because our founders were doing some great projects, but realized that 6 months after they left, things had changed at the plant, and they soon fell out of optimization. So they set out to build a product that would deliver persistent results and savings. If you only optimize once and not continuously, not dynamically, then you're just making the HVAC system more efficient at a given point in time instead of over the long term. We're on the correct slide right now. No, go back one, please. What is optimization? Going back to the question of defining optimization, it's about making the whole system as efficient as possible and doing it in a way that is sustainable over time. This incorporates everything from the initial design of the HVAC system, including infrastructure and what components you use. A lot of people focus on how efficient their chiller is or their pumps, but are they including the right sensors or accurately measure those pumps? Are they designing the system for future expansion from the get-go? It's also about how you operate your plant once it's built. Are you using enough automation or the right automation? Or are you still staging chillers manually, for instance? And finally, are you maintaining your HVAC system properly over time? Are you doing the right maintenance at the right time? Are you properly measuring the efficiency projects that you are doing to make sure they're getting the intended results? Ultimately, when considering optimizing your HVAC system, you really need to take into consideration all of these different factors: how you design your HVAC system, how you operate it, and how you maintain it. Next slide, please. This is what we call the chiller plant efficiency scale. I mentioned measurement in the last few slides. And when we talk about the optimization of chilled water plants in particular, there's a metric that we like to use, which is kilowatts per ton. Think of it like the miles per gallon of your HVAC system. Some people just look at the kilowatts per ton of individual components. But given our focus on systems, we think it's very important to look at the total efficiency of a plant, including chillers, tower fans, condenser water pumps, and chilled water pumps. And as you can see from this graph, you can get a pretty good idea of how your plant is performing relative to others by seeing where you fall. Red being very inefficient at greater than 1 kilowatt per ton. Note that we've seen some plants pre-optimization that were as high as 1.8 kilowatts per ton. On the other end of the spectrum is what you'll generally see from ultra-efficient data centers that companies or Facebook will build themselves. Next slide, please. As I mentioned in the last slide, we often use the analogy of miles per gallon to explain kilowatts per ton. I think this extension of that analogy is pretty powerful. Imagine you have a Hummer and you must drive 100 miles. This represents the total heating and cooling load of a building. Click twice, please. Chiller optimization turns your gas-guzzling Hummer into a super efficient Prius. So you're going from 10 miles per gallon, basically using 10 gallons to go 100 miles, to 40 miles per gallon, using only 2.5 gallons for the same distance. Click twice, please. Now, adding airside optimization to the equation makes things really interesting. What you're doing is reducing the load on the building. In other words, how much cooling it actually requires. That's like being able to reduce the number of miles that you have to drive from 100 to 60. So not only is your car running much more efficiently, but you're not driving quite as far. Next slide, please. Okay, let's take a look at the typical architecture for a system like ours. This is a sample, and if you'll notice on the right, the green box, let's start there. This is where our operational modules reside, and it's typically located on site. They connect into your building automation system and act as a supervisory overlay, reading data from the BAS about the device layer, and then sending commands back to the BAS to execute. There is also a cloud-based layer that can provide analytics and reporting, measurement and verification, and sometimes take advantage of things like machine learning for even more advanced functionality, like automated chiller staging or predictive free cooling. And all of this happens much, much more quickly than humans could ever handle. Next slide, please. The next two slides give you a sense of how software-based HVAC optimization can work, in this case, using what's known as relational algorithms, which look at the relationship of all components to each other. It then decides on the most optimal way to run each piece of equipment in order to optimize the entire system. In all variable speed central plants, each piece of rotating machinery represents an individual energy input that results in a different output. For chillers, additional energy results in colder water. For condenser pumps, additional energy results in additional condenser water flow, which lowers the chiller's lift and results in additional cooling for any given chiller energy input. Additional energy input to the cooling towers results in lower condenser water temperature, which lowers lift and increases cooling output. Additional energy input to the chilled water pumps results in a greater volume of chilled water delivered to the building. Click, please. What optimization does is look at all of these energy inputs, as well as the total system cooling output, and determine how best to run each component to make the whole system as efficient as possible. So, same cooling output, but lower energy input. It might seem counterintuitive, but it's not always run everything slower. Sometimes optimization can lead to a component level increase, say a faster pump speed, for instance, to ensure an overall reduction in total system energy. Next slide, please. There you go. When you're optimizing air handling units, or AHUs, optimization looks at like reducing the amount of air and using a slightly higher temperature. This not only means less energy used in the air side, but it results in less chilled water required. This results in energy savings on the chiller and can also eliminate reheat out in the zones. Once again, though, the key is the same total system output with a lower system energy input. Next slide, please. What are the benefits of optimization? Now that we've gone over what optimization is, let's talk about what it can do for you. I've mentioned saving energy, money, and carbon from optimization. These savings can be impressive. In our projects, we typically see ROIs of 2 to 5 years, although this can vary, of course, depending on things like local climate and electricity prices. Also keep in mind that we carry the cost of equipment or facility upgrades in our calculations. But the benefits of optimization go beyond saving energy. Obviously, carbon emission reductions go hand in hand with energy savings, but HVAC optimization can also be a huge water saver. As we've discussed, optimization, especially software-based, can mitigate performance drift that occurs over time. The improved visibility into your HVAC system that optimization provides can help you improve your overall operations, and importantly, it allows your facility staff to focus on other things. Next slide, please. When you're looking for an HVAC optimization software vendor, what are the things you should look for? Well, as with any product, make sure you choose someone with experience in HVAC optimization that can provide you with references and case studies of work in plants similar to yours. You want a solution that's modular and scalable to fit your needs across your campus, whether that's a central plant or distributed chillers, AHUs, labs, what have you. You want someone that is going to provide you with a fully automated measurement and verification system, so you can always be sure that you're saving as much as expected. A lot of facilities don't have the luxury of having all equipment from the same brand, so you want someone that is BAS and HVAC equipment agnostic and that works with any technology, whether it's BACnet or Modbus. If you remember the Hummer and Prius example, you ideally want someone that can help you with your chillers and your air side as well. A detailed baseline goes hand in hand with automated M&V. You're definitely going to want someone that has a great engineering and technical support staff to help you through not only your optimization project, but to help you make sure you stay on track as time goes on. And that leads to the last point. You want to make sure that you're going to get persistent long-term savings out of your HVAC optimization. Otherwise, you'll find yourself doing it all over again a little ways down the road. Next slide, please. So why software-based optimization? I just want to reiterate some of the reasons, as opposed to a purely engineering-based solution, or even just relying on your BAS system. The fact is, building performance degrades over time. The typical traditional commissioning service can get buildings in shape and running relatively efficiently, but as soon as something in the building changes, you've got to start it all over again. Even so-called continuous commissioning keeps you on target, at best. But a true software-based solution not only fights performance drift, but it can actually help you reduce your operating costs over time by running your HVAC equipment as efficiently as possible. by giving new insights into your facility and the tools to run your operations more efficiently. Next slide, please. Okay, with that, I'd like to turn it over to Kevin Koretich, our Director of Optimization Services. He will take you through a few real-world case studies of how software-based HVAC optimization has helped some of the premier universities in the U.S. get closer to their own sustainability goals. All right, Kevin, take it over.
Okay, thank you. Go ahead to the next slide. So the first case is Baylor University in Waco, Texas, and I went in there about 2 years ago to optimize their chiller plant. Next slide, please. So they, excuse me, sorry, I have to get something out of the way. So they have a, Baylor's operated by a third party, their utility system or their central plant. And so they have a goal of reducing their cost, energy reduction of 1 million by the end of a 10-year contract. As with almost every campus, cooling all year round. The original plant had 7 chillers, a mix of every kind of chiller imaginable. And then in October 17, we installed a new 2,700 ton variable speed chiller. So the very beginning, with just the 7 chillers, installing software-based optimization, we were able to achieve a significant improvement. So this was no new equipment. This was just software only. We were able to improve their kW per ton by 17%. In 2016, we saved nearly 5 million kilowatt hours and reduced their CO2 by 7 million pounds. Since we installed a new chiller, or Baylor installed a new chiller, in October of 2016, we have been able to increase the savings because we can now base load this chiller. We've increased the savings to 651,000 kilowatt hours just since that time. And our average plant performance has, again, improved dramatically, especially during times when we can run just that single chiller to meet the load. Next slide, please. So when we went in, we do an engineering site assessment. And so on the left-hand side by month, you'll see our estimated ton hours, our estimated plant kW, and our estimated plant kW per ton. That is how we build a baseline. Then we project the performance that we hope to see. And then there's the actual performance. In this case, again, a 17% improvement. Why didn't we meet our goal of 0.724? It's an old plant, and many times pieces of equipment that we needed to run were not operable, and so in that case, we lose some efficiency because we can't run either the equipment we want to run or the number of pieces of equipment that we want to run. Next slide, please. We of course do, so we bring all the data from the chiller plant. So all the control is done on site locally with our controller. But in addition, we pull data up into our servers in the cloud and build some graphics that the operators can use. And this is a couple of this is a screenshot of one of the graphics that the operators use from our website. And basically what it's telling them is positions of their valves, what they should be at. And of course, we're controlling that. They're just making sure that they're able to see that it's following what it should be doing. We're telling them what their current load is, when we're going to add a chiller, when we're going to shed a chiller, and then we would give them the time to add or the time to shed. And we do that so, especially for plants that operate 24 hours with somebody in the control room watching the control system, so they're not taken by surprise when a chiller adds or sheds, or if they're sitting there wondering, oh, when are they going to add a chiller, or when are they going to shed a chiller? So we provide that graphic for the operators to keep them informed. Next slide, please. So just in summary for the Baylor system, we integrated, so our controller can integrate to pretty much anything. We integrated in this case to a Siemens Apogee BAS using Modbus RTU. The BAS network, their infrastructure there is very poor. So our pump control, which we're trying to look at differential pressures all over campus and control to the minimum differential pressure, a lot of times would go stale, and we had some difficulty around that, but we were able to resolve that. And again, you have a whole bunch of different types of chillers. They all have different pressure drops. They all have different operating needs. So that was something we had to deal with. A benefit was by looking at all the differential pressures and actually trending them, we were able to determine which buildings were causing the big pumps in the central plant to operate at a much higher pressure than they needed to. So the Baylor went out and installed smaller pumps around in some of the buildings. And I showed you our web platform was used by the control room so that they understood the operation. And in the end, it was a very successful project. Next slide, please. So this is UT Austin. So this one's a little different because for the first half of this, I worked for UT Austin. Actually, for most of this, I worked for UT Austin, so I'm very familiar with it. Next slide, please. UT Austin consists of 4 chilled water plants, 45,000 tons, and it's on a common loop with a thermal storage tank and about 6 miles of chilled water piping. The first interaction with Optimum Energy was we constructed a new 15,000 ton plant with 3 variable speed dry 1,000 ton chillers. And then we started working on control of basically a dispatch model for all 4 chiller plants for optimizing which chillers to bring on when and how to control DP. In the end, we had some very good luck. We saved 21 million kilowatt hours a year in energy. We had a kind of a surprise for all of us by doing much better DP control. We significantly reduced steam usage, and that was because some of our older valves, when we were operating at high differential pressures on the chilled water loop, had a lot of blow through, and so we were simultaneously heating and cooling. And then the reduction in tons or kW consumed at a chiller plant obviously results in water savings too. a large improvement in the chiller plant kW per ton. And again, part of that was software. Part of that was that we had 3 brand new chillers that were variable speed, and we had no variable speed chillers prior to that. Our peak summer kW was reduced by 5 megawatts. The 15,000 ton plant itself, for in the wintertime, it was able to run, we got it down to 0.35 kW per ton. In the summertime, it was up around 0.65 kW per ton. And as I mentioned previously, the more sophisticated DP control that we did with the total campus dispatch model not only reduced pumping kW, it significantly reduced steam use, especially in the summertime, where we have a steam load because it's Austin, but we do have a little one, and this really cut it. It cut it from 50,000 pounds an hour to 30,000 pounds an hour for the entire summer, which is very significant. Next slide, please. So this was a phased installation. The first was the new chiller plant, the installation of what's called optimum loop on that plant. The next is what we called sweet spot optimization, which is basically trying to maintain station 6, which has the variable speed drive chillers in it, at about 85% load, which is the best load to the most efficient place to set a variable speed drive chiller, somewhere between 70 and 85%. We added the TES into the dispatch model, again, to try to delay having to bring on a second station, trying to run the new variable speed drive chiller station as much as possible. Then up in our Pickle Research Center, we installed optimum loop on a 3,250 ton chiller plant for the high performance computing facility. And we're currently working, now that I'm at Optimum Energy, I'm currently working on chilling station 5 and bringing that into the total campus chiller dispatch. Next slide, please. So again, I was there when we designed the chiller plant, and I worked closely with Optimum Energy and one of their main players at the time to design this station to be optimization ready. I got a lot of pushback from the design engineers, but eventually won out, I guess, because I was the owner, so I have a little more pull when I'm the owner than the contractor. In the end, there was only one mod valve. All valves were line-sized butterfly valves. There was only one valve that had to modulate. It was one on one of the tower cells to equalize flow over the cells. So we had 3 identical chillers, 4 identical chilled water pumps, 4 identical condenser water pumps, and 3 identical cooling towers. So we could, and everything was headered together so we could run any chiller with any pump with any tower. So it was really a good project, and we paid back the cost of the software in the first 4 months of operation, November through February. Next slide, please. This again just goes through the sweet spot control. I won't go into it too deep or I'll run out of time. But again, what we did was we tried to keep chilling station 6 at a constant flow, constant load, because that's where it was most efficient. We did some hydraulic modeling and found the most 7 hydraulically remote differential pressures on campus, and we brought those in. However, which differential pressure we controlled to was based on which chiller plants were on, because the minimum DP switched with chiller plants. We started with chiller station 3 because it had variable speed chilled water pumps. It was the only one that did. No other pumps at the time had variable speed drives on them at the other 2 chiller plants. Once we proved that concept, we added in the TES charge and discharge, again, to kind of keep, again, the first goal was to keep a constant speed plant from having to come online, so you could charge the TES at night with station 6 when the load was low, and then you could discharge during the day to keep from having to bring on another plant. Now the university is installing variable speed drives on the other large plant there, which is chilling station 5, so that it can be added to the dispatch model. Next slide, please. Here we use, we connected to an Allen Bradley system, PLCs. We use Modbus TCP to communicate. Again, our controllers live on site. In this case, something we don't recommend, but what we did here was we use an open loop control rather than closed loop for staging chillers and pumps. So the automation system doesn't bring on a chiller when we tell it to. We tell the operators it's time to bring on a chiller, and then they bring on the chiller, and the same with pump staging. We don't recommend that, but it is possible to do. Again, the dispatch logic is, for the entire plant's going to be quite the challenge, but it'll be a lot of fun. And we've been able to, with the TES, about 4 months out of every year, we're able to run just the variable speed plant and the TES, and that keeps our KW per ton there very low. And again, controlling the chill water differential pressure in a smarter fashion just had all sorts of benefits, including not ruining valves and me getting yelled at by the folks on the facility side. Next slide, please. Last case is Columbia University. It provided a challenge in that it's dual fuel. So we have steam centrifugal chillers as well as electrical centrifugal chillers. They have significant demand penalties there for running electric chillers at certain times, so we have to switch to steam. So we came up with a new method of looking at performance, because KW per ton really wasn't the driver anymore. We started looking at dollars per ton for this particular site. That was what seemed to make the most sense. Next slide, please. So this is just real briefly. It's a large, very large system, 14,000 ton peak load, all sorts of chillers, both steam and electric, mix of sizes, mix of manufacturers. We did this in a multi-phase approach. We first installed a controller and started to monitor and collect data. We began with the open loop control method, which I discussed before, because that's what they felt comfortable with. And then now we've moved to a more of a closed loop control. The operators still start chillers and stop chillers, but that's the only thing that's not closed loop on that system. The total savings in the first year was $1.1 million. It's been significant what we've been able to save there, and one of the big things we did there, not only did we cut the total plant power consumption, but by reducing the differential pressure and how they measured it, where they measured it, and how they controlled it, we basically cut the plant base load in half. They used to have to, their delta T was about 4 degrees. And so they had one chiller running and one chiller open so that they could move enough water. And we were able to correct that so that they didn't have to do that anymore. Just at certain times, they still have to do it. But it's, again, it was a huge reduction at base loads. Next slide, please. So again, we went to a $1 per ton because, again, we can't use kW per ton, we can't use COP. We started out, you can see the different phases. We started out at 0.184, then we moved to 0.163 with the full open loop, and then a little more modifications. We got down to 0.134, so 13.5 cents per ton, and then finally when we were fully completed with our system there, we were down at a little less than 12 cents per ton. So a huge drop in energy costs, over 36% reduction in costs. And again, it was because it was mixed. I included in this because it was a mixed fuel plant, just so you could see how we deal with a mixed fuel plant. Next slide, please. And here's what we provide the operators for chiller staging. And again, this tells them our various set points and conditions for staging up and staging down chillers, so they're not in the dark as to when we're going to ask them to stage up a chiller or stage down a chiller, or which chiller we're going to ask them to stage up or which chiller we're going to ask them to stage down. So again, this isn't part of their VAS system. It's part of our system in the cloud that then they can display on a web browser in their control room. This is proven. This is not the only place that we've used this. This is proven to be a valuable tool for operators. They like to know what's going on, and obviously I don't blame them. I would want to know what's going on too, and so we found this to be very helpful. Next slide. Again, this was an Allen Bradley system, mixed fuels. Again, when we don't do a fully closed loop control, it's a bit more challenging, but it can be done. And they're actually using the energy reports that we provide them to determine their chilled water pricing to campus. So their utilities department uses that because they charge the individual departments for chilled water. Again, overpressurizing the system kind of seems to be a ongoing issue for any large campus that you look at, and being able to look at that and reduce that in an intelligent way, where you're still providing chilled water where it's needed, but not, again, taking valves off their seats, or if there's, old campuses have three-way valves all over the place, so you're not bypassing, just a whole bunch of water and getting delta T's that are 4 or 5 degrees. is you can't really measure how big the benefit is of that. That's huge. Next slide. And I guess that's it for me. And I think it's time for questions then.
Great. Thanks, Kevin and Kevin. That was great. So we have several questions that came in. Let's see. I'll start with a very simple one, which I think you've probably answered over the course of the webinar, but maybe just detailing it a little bit again. So someone asks, aside from efficiency of changing the set points and changing run times and occupancy sensors and things like that, what's the next step in efficiency?
So we're talking about two sides now. So if we look at just the chiller plant or the supply side, we have these relational algorithms that look at the chiller kW, and using the chiller kW, we're able to calculate condenser water pump speed and a cooling tower fan speed. So we're not controlling to a cooling tower or condenser water supply temperature set point. It's not a P&ID, it's a strict formula. And using that formula, those actually two formulas, and running the condenser pump at that speed and the cooling tower fan at the speed provided, the kW of those three pieces of equipment, the chiller, the condenser pump, and the cooling tower fan, is as low as you can get it. You can't, this was proven by the person that came up with these, who's much smarter than I am, and patented. You cannot get lower than that for the three pieces of equipment. Now you can say run your fan harder and your pump harder, and you can reduce your chiller kW. But then if you look at the sum of the three kWs, it's higher. And the best way I can think of to explain it is if you're running your cooling tower, obviously you want as cold a water as you can get to reduce your chiller lift without going too cold for that particular chiller. But there comes a point at which increasing your fan kW doesn't have an impact, or as much of an impact, on your chiller kW. So you might increase your fan kW by 50 kW, and you might only reduce your chiller kW by 30. Well, obviously you've just increased your total system kW by 20. So we use these for that side of the system. DP control is pretty straightforward. There's no magic. It's just understanding what you're doing. On the building side, we use psychometrics basically to reset supply air temperature, supply air humidity, try to minimize fan speeds as much as possible by using these psychometrics to put out the right temperature and hopefully reduce either heating or cooling. One example I can think of right off the top was a place that was doing simultaneous heating and cooling. It was a large pharmaceutical place, and we just were able, using our psychometric chart, basically to find a point where we could completely close the heating valve. We still needed chilled water, but not as much. So we took the chilled water valve from 80% open to 50% open or 40% open, and we took the heating valve from 20% open to close. And we didn't touch the fan speed on this particular one. It was just really using psychometrics is all it was. So we attacked the demand side in a lot of different ways. But a lot of it revolves around using psychometrics to try to minimize how much heating and cooling you need, and also use them in a way that we can reduce fan speed if at all possible.
Great, thanks. Do these kinds of solutions work on smaller campuses, 2,500 students, 10 to 15 buildings, that kind of a scale?
In the chiller plant, yes, for sure, because we've done chiller plants at smaller places than that. So yes, they do work on that. On the air side, it kind of depends on the size of the buildings and the use of the buildings. We look for buildings, for this to really work, you want a building probably that uses a lot of outside air. You want a building that operates 24 hours a day, 7 days a week. So in an office building that's closed in the evenings and on the weekends, while you can get reductions, it's, your payback's a lot harder, right? Because you don't have that many operating hours. And if you have very small systems, there's just not as much you can do on the demand side in that case. But on the chill water side, yes, we've got some pretty small installations, not just on like medical campuses where you have a hospital and a couple medical office buildings, or a small pharmaceutical plant. Chiller plant still works great. Sometimes the HVAC can work, and sometimes it doesn't. Just doesn't make sense.
Mm-hmm. Okay, another question we had was, can you use balance of plant control systems with renewable energy systems?
Yes. So we're working right now on a system like that, that has a combined heat and power. So it's got some on-site generation along with some heat that it's putting out, and they've been using that heat in absorption chillers for a while, and we think we have some better uses for that. But we can also do it for demand limiting from a utility standpoint. If you're looking at, sometimes when you have on-site generation, there are times when you can buy power cheaper than you can generate it, and so that all comes into the optimization as to what rules do we use to determine how we dispatch things, and so that varies widely from one site to another. But yes, the answer is yes. That was a long answer, but yes, the answer is yes.
Okay. So for the case studies you discussed, how many of them were a one-time intervention versus the ongoing software system?
So Baylor was probably the closest to a one-time intervention. Mm-hmm. The initial plant at Baylor was a one-time intervention. And then about a year and a half after the one-time intervention, they added another chiller as part of their energy reduction goals. So we had to go back, obviously, to bring that new chiller into the software. So Baylor was pretty close to one and done. That's probably not a very good way to put it, but we only went out once for Baylor originally, and we didn't go back until the new chiller went in. And had they not put in the new chiller, we wouldn't have went back. There wouldn't have really been a need to.
Let's see. So I had a question about BAS. So are there ways to better utilize building automation to optimize HVAC?
So we do try that, and again, you can use building automation. You can just use general rules, right? That you can look at. Okay, if you have the data and you have a big air handler and it has a whole bunch of VAV boxes, and if you can get the good data, which is many times a problem because a chiller plant has a lot of data, but nowhere near the amount of data that an automation system has in a bunch of buildings. It's orders of magnitude different. If you look, you can look at, from a software side, you can look at, okay, how many zones are my VAV boxes wide open, and how many zones are my VAV boxes pinch closed? So an wide open one we might call a starved VAV, starved box, and a closed one would be if it's too far closed, we have too much duct static pressure, and so what we really want to strive for in a case like that is much like we do on the chill water side, where we don't want any valves wide open, not making set point. We'd like to see all our valves, or our most wide open valves, at maybe 80%. So they still have some controllability. Well, the same thing with VAV boxes. Is there a way using temperature reset and supply pressure reset to perhaps get to the point where we can reduce fan energy and cooling or heating by looking at those VAV box positions and doing some math with all of them. And really the biggest difficulty we've had there is it's just so much data that you're relying on to be correct. It can be a challenge because it's a lot of times not all that data is intact. Maybe with the new system it is, but some of these older systems that have been grown over the years, which many people have, it can be a real challenge, but it is possible. So those are some things that you can try to do with your BAS system. Is okay, how can I adjust my set points, supply air temperature or return air temperature or whatever, and then look at my box position and maybe run, when can I drop my static pressure down? And when do I need to raise it up?
Mm-hmm. All right, I think, okay, I think we're running out of time, so I think we'll just wrap it up now, and people can contact us if they have additional questions that we didn't get a chance to answer. So I just want to thank everyone again for attending, and to thank our presenters for taking the time to be with us today, and remind everyone that the slides and the recording will be available in the next few days on the Second Nature website.